Okay, guys, what's up? Welcome back. So hopefully you saw the announcement. There was a very slight typo in the last lecture. That's what I get for trying to take my handwritten lecture notes and turn them into nicely typed ones using ChatGPT. Occasionally a tiny thing gets missed. So I've fixed that in the videos. Check the announcement. Everything should be fine now, but I want to make sure that nobody missed out on that little piece there because that could cause some confusion. So check the announcement. Everything should be good. But today we're getting into section 1C, and we're going to talk a little bit about subspaces. So we've defined this object called a vector space. A vector space, if you want to think about it kind of intuitively, models the basic behavior of what happens when you take multiple copies of a field and you put them together and you try to extend the field operations in kind of the most obvious and natural way possible. So we've got vector spaces, and the first thing we're going to do to try and understand what vector spaces are like and how they work is we're going to, well, and this is a theme that we'll see throughout the class, we're going to try to understand how they work in relation to each other. So this might seem a little bit weird the first time you see it, but this is a very heavy theme throughout mathematics, which is that if you have an object, one of the best ways to understand how that object works and what that object is by seeing how it maps to other objects in ways that preserve its structure. So in particular, if you have an object, you can see how a given object in that class of objects can be mapped to another object in that class of objects while preserving the structure of the object itself. This sort of way of looking at things in terms of their mappings between things with similar properties is just really everywhere in mathematics. So maybe this seems weird at first, but we'll get into it a little bit. I'll try to give a little more intuition, and this big theme will keep popping its head up throughout this class. So here, let's just start it off. Let's get used to it, and let's get going. So first definition is a subspace. A subspace is a subset of a vector space that is also a vector space with the same additive identity, the same addition, and the same scalar multiplication. Here's the way you can think about it in your head. You've got a vector space V, and then inside of it, you've got a little vector space U. So you can grab plenty of different chunks inside of a vector space, but not all of them are themselves vector spaces. Those little vector spaces inside of a big vector spaces, we're going to call subspaces. So subspaces, little vector spaces inside of big vector spaces. So let's talk through our first little theorem. So conditions for a subspace. A subset U of a vector space V is a subspace. So a subset is a subspace if and only if U satisfies the following three conditions. First off, you have to have an additive identity to be a vector space in the first place. And if one of our conditions to be a subspace is that we have to have the same additive identity, then certainly the additive identity of the larger vector space has to be a member of U. So that first condition makes sense. The second condition is closure under addition. This makes some sense because we have to have a binary operation on U that is a map that sends two copies of U to U. So if we're going to take the addition from V, which is a binary operation on V, and restrict it to U to find an addition on U, well then, if I take two things in U, I certainly have to send them to something in U. That is, if I pick, here I'll draw a little picture. If I pick two things inside of U, here's thing 1 and thing 2. Let's call it little u and little w. And this is sitting inside of V. If I add these things together, I want to make sure that I don't get something like this, where u plus w sits outside of big U. So this situation right here is exactly what we have to avoid. This, no way. None of that. All right, so from there, we only have one more condition, which is basically the same thing. just with scalar multiplication now instead of addition. This says closure under scalar multiplication. So if you take an element of the field and an element of your subset, then any scaling of that element is in the subset. That is, if I take the field element and the element of the subset, and I scale the element of the subset by the field element, then I get back something that lives in the same subset. If these things happen, then U is a subspace of V. And conversely, if U is a subspace of V, these things happen. So I claim this, the proof here is so simple, let's just sketch it. So if U is a subspace, then I'll say this holds by definition. So that is, if U is a subspace, then the existence of an additive identity is implied by the definition of a subspace. It has to have the same additive identity, so obviously the additive identity has to be in there. It has to have the same addition, so obviously if it's going to have the same addition, then that addition has to be a, if it's a subspace, then that addition is a binary operation. Okay, and that implies the second condition right there. Since if this lie outside of U, it would not be a binary operation on U. Finally, same thing with scalar multiplication. If it's a subspace, then scalar multiplication is a map from the field and the subset to the subset, or the subspace in this case, since we're assuming it's a subspace. So closure under scalar multiplication is a necessary condition of it being a subspace. All right. In the reverse, I will say it in the shortest and easiest possible way. Notice that any of these being violated would prevent U from being a subspace. Moreover, they are precisely the three conditions defining a subspace. So that's not a very thorough proof, but it really is essentially exactly as easy as you think it is. So we have three conditions right here describing when a subset is a subspace. And would you look at that? 1, 2, 3 conditions right there. So those are exactly the same conditions. It is extremely routine to just verify that having the same additive identity, the same addition, and the same scalar multiplication, that is these conditions. All right, cool. So we're making sure that, hey, if it's a vector space with these things, then all of that holds. And if these things hold, then it has the same additive identity, the same addition, the same scalar multiplication, and satisfies all the conditions of being a vector space. So, cool. Now, looking at little vector spaces inside of big vector spaces, it is useful to have some basic conditions to check, some easy ways to identify whether or not this is the case. But the reason we care about it is, like I said, because we're going to look at how you can map little things to big things and big things to little things. Think of it somewhat like this. Though this is not a perfect analogy, it is kind of similar. If you want to understand how, division works for integers, positive integers, counting numbers, then that is basically the same as understanding factoring. So if you want to understand how the whole counting numbers work with respect to, say, for example, the operation of multiplication, then that amounts to understanding how you can break down a counting number into smaller counting numbers using that operation. That is factoring. So we're going to do something basically analogous to this with subspaces of a vector space. That is, we're going to start to look at, hey, how can I take little vector spaces inside of a big vector space and map them to, and build other vector spaces, map them to other vector spaces. So we'll take these little building blocks, these small vector spaces inside of a larger one, and we'll see how we can fit them together to make other small vector spaces inside of that larger one. So basically we're saying, hey, you can have a vector space with little chunks in it that are also vector spaces. Now we'll ask ourselves, how is this larger chunk built out of the smaller chunks inside of it? This gives us, one of the easiest ways we can do this is with this definition. So if you have a collection of m subspaces of a vector space V, then the sum of those subspaces, which we will denote by V1 plus so and so on up to Vm, this just the subspaces with pluses in between them. This is the set of all possible sums of elements in each subspace. More precisely, the sum of V1 through Vm, subspaces here, is the set of little v1 plus all the way up to little vm, the sum of elements of each subspace, where v1 is in v1, v2 is in v2, and so on, all the way up to vm being in vm. So it's just sums. Okay, cool. So we've got direct sums. We've got some subspaces. Let's do an example to kind of make this a little bit clearer. So let's take U to be the subset x, x, y, y in F4, so 4 copies of some field, such that x and y are just elements of F, the field. So this is all subsets of F4, 4 copies of a field, where the first 2 things are the same and the last 2 things are the same. All right, cool. Is this a subspace? Let's think about it really quick. So going back up to our theorem, is the additive identity in there? Well, that would be the vector of all zeros in this case. So if x is equal to 0 and y is equal to 0, then this is the vector of all zeros. So certainly the additive identity is in there. Is it closed under addition? Well, if I take 2 vectors like this and I add them together, obviously I will get the same thing in the first 2 entries and the same thing in the second 2 entries. Notice, basically, what I'm saying is, here, I will write that because it is probably slightly clearer to see it directly. So I'll say x1, x2, y1, y2. Or even easier actually here. Let me change my notation slightly. x1, x1, y1, y1 plus x2, x2, y2, y2. Something like this. If I add them together, then I get x1 plus x2, x1 plus x2, y1 plus y2, y1 plus y2. And notice this guy is an element of U. This guy is an element of U. And since the first 2 entries here are equal and the second 2 entries are also equal, this guy out here is also an element of U. So naturally, it is closed under addition. Nice. Closure under scalar multiplication can be shown in exactly the same way. It's even easier. Basically, just if the first 2 things are exactly the same and the second 2 things are exactly the same, then if you multiply all of them by the same field element, you will still have the first 2 things being exactly the same and the second 2 things being exactly the same. All right, cool. So U is a subspace. Here is another subspace that basically works in exactly the same way. Let's call it W. Let's make this into, say, x, 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 y in F4, such that x and y are elements of the field. Then this is also a subspace for the exact same reasons U is, just make it the first 3 arguments instead of the first 2 are exactly the same. Now, if I take U and I sum it with W, what I get out is I get out x, x, y, z in F4, such that x, y, and z are in the field. Why is this? Well, if I pick some stuff, here I will do a slight erase right now, just to make everything a little bit easier to see. So here I will just use this exact thing right here to make my life slightly easier. And I will now make this, instead of a y2 right there, I will make that into, oh, I want my pen, not, so I'll make that into an x2. So this is something in u, this is something in w. And if I add them together, then I will get, now instead of a x1 plus x2, x1 plus x2, y1 plus y2, it will now become y1 plus x2. Okay, so this is the same as this. This could be something else, and this could be something else. So, same, and these things are maybe different. Hence, two things are the same, the other ones could be different. All right, look at that. It's also a subspace, isn't it? Very cool, just for the same reasons that U and W are. All right, so you can take two subspaces, you can put them together, and you can make something else. In this case, that other thing turned out to be a subspace. Let's look at some more facts and see if we can prove that this is always the case. One tiny bit of notation. So, if we have a subspace U of a vector space V, we write U less than or equal to V. This is basically, if you want to think of it, this is like that, so that U is a subspace. Here's the way to think of it. So you can certainly have subsets U of V. When we put the slightly sharper looking symbol, we mean that it's like a slightly more precise kind of condition. So there are many subsets, and not every subset is necessarily a subspace. The particular case where it is, we will use this symbol. So just a tiny bit of notation. I will do that to keep myself from writing subspace every single time. Say, you know, let U be a subspace. Instead, we could write, suppose U less than or equal to V. All right, cool. So here's the statement of the theorem. Let's suppose that V1 through Vm are subspaces of V. Then what we want to claim here is that the sum of V1 through Vm is the smallest subspace of V containing V1, containing V2, all the way up through Vm. So let's prove it. That is, what we're trying to say is that the sum of subspaces is the smallest subspace that contains all of the summands. So an easy way to visualize this is that if you have your big V here, and you've got your, V1, your V2, your V3, then if you want the smallest subspace containing all of them, it's like the tightest little envelope around all of these guys. This is V1 plus V2 plus V3. So this is kind of a good example of what I mean of understanding what V is in terms of the little pieces it's built of. So here we're taking little pieces and we're saying, look, I can put them together, and what I get is I get another little piece that has the nice same properties, and moreover, I get the smallest such little piece. Kind of nice. Okay, so here, let's prove this. I claim clearly Vi is contained in the sum of V1 through Vm. Okay, fair enough. Since I will write it this way, So here's what I'm trying to say. Since if you take the element of the sum of v1 through vm, that is just all zeros except for vi, except for the ith coordinate, which is any element of vi, then that is certainly in there, right? You could sum up only zeros on everything except for the pieces that come from vi, the ith element of the sum. And then since you could do this for every item in vi, you certainly get all of vi being contained in that sum, since 0 is the additive identity. That is, this right here is equal to little vi. Okay, nice. Conversely, if W is a subspace of V such that VI is a subspace of, or is contained in, I won't even say is a subspace of yet, is contained in W, for I equal to 1 up to M, for all the i's, I need a comma after that, then V1 plus Vm, all the way up through Vm, is contained in W as well as subspaces must contain all finite sums of their elements. That is, subspaces are closed under addition. So if each vi is contained in W, then take a thing from V1, okay, cool, that's in W. Take a thing from V2, okay, cool, that's in W. Add them together, it's got to be in W. Then take something from V3, add it to the previous thing, and so on. And the next thing you know, you've got sums where each element is a member of, each element of the sum is a member of the corresponding subspace Vi. And since that has to be in W by the closure under addition, which follows from W being a subspace, then it contains the sum. Cool. All right. Relatively straightforward. What do you think? Not too bad. Okay, so we've seen subspaces. We've seen that we can take these little building blocks and kind of put them together to build a bigger subspace, and it had this sort of nice symmetry to the whole thing. That is, you took some subspaces and you could build a bigger subspace out of it, and that subspace was the smallest such subspace that contained all of the little subspaces. So let's break it down a little bit further, and let's see if there's a very, very nice version of this. I'll explain more in a moment. So the direct sum is a type of sum. It is a particular case of the sum that we just defined, and it is a distinguished case. So if V1 through Vm are all subspaces of a vector space V, then the sum of V1 through Vm we'll say is a direct sum if each element of this space can be written in one and only one way, as a sum of elements from each corresponding subspace. So it could be the case that you have a sum that is not direct. So that is, you have a sum of things, and there is more than one way to write an element in the sum as a sum of VI's, where each VI is an element of the subspace big VI. Okay, it's possible. It could happen. For example, let's let U be a subspace of V. Then, this is an example, just to be clear, U plus U is not direct. Do you see why? If W is in U plus U, then notice that W is in U, so W equals 0 plus W, which equals w plus 0, i.e. w equals u1 plus u2, which is equal to u1 prime plus u2 prime for ui prime not equal to ui. That is, there is more than one way to write any element of u plus u. All right. Well, I guess I should be clear. Let me make sure that this is not the trivial subspace. So I'll say not equal to 0. So if this is the trivial subspace, then we have to be a little bit careful, since in that case, this would be 0 plus 0 equals 0 plus 0, and you would have u1 equal to u1 prime and u2 prime equal to u2. So I should be clear that if it's a non-trivial subspace, so not the 0 subspace, the subspace with only the additive identity. All right. Well, if we've got a direct sum, it'll be handy to have a nice notation to represent this. So if you've got a direct sum, then we're going to just circle all of those pluses to denote that it's very special. So this just says, hey, if I use this circled plus, this is just an indication that it's a direct sum. That way I don't have to say, let the sum v1 plus ... vm be direct sum. Instead I can say, suppose this, with the pluses, suppose this is a direct sum. Okay, cool. So when is something a direct sum? Well, this will be a very important result for us. All right, so let's suppose that v1 through vm are subspaces of v. Then we'll say that the sum of v1 through vm is a direct sum if and only if, in both directions, the only way to write 0 as a sum, where each vk is an element of vk, is by taking vk equal to 0. This is nice. This basically tells us something really cool, which is that instead of having to check every possible element in this sum to confirm that this sum is direct, instead we only have to check a single element. That is way more convenient. That is a dramatically less amount of work. For example, if these are, something like subspaces of like R7 or something like that, right? And they're like two-dimensional subspaces, from regular old linear algebra world, right? Then you would have to check infinitely many sums if you went through and checked all of them, right? This is a big time saver, and in fact makes tasks that would otherwise be impossible, since you can't enumeratively check out every single thing, very possible, and quick even, since you only have to check it for 0. So let's prove it. Now, if v1 plus vm ... is a direct sum, then since 0 equals 0 plus all the way up to 0, we get that, or I'll even say it easier. Instead of that, I'll say we get our desired result. Okay, so if we have a direct sum, then the definition of a direct sum says that each element can be written in only one way as a sum of the elements of each subspace. So if this is a direct sum, then because I can write 0 in this way, that is the only way I can write it. So I get my desired result. If this is direct, then the only way to write 0 as a sum in this form is with each of those things equal to 0. Cool. In the other direction, now suppose the only way to write 0 in this sum is as 0 plus ... all the way up to 0. And I'll say i.e. 0 equals v1 plus vm implies vi equals 0 for I equal from 1 all the way up to m. Okay. Now, suppose W equals V1 plus Vm, and W equals V1 prime plus Vm prime for some W in V1 plus Vm. Okay, so now suppose that I can write W in two ways, not necessarily different, but just in, two ways using some symbols. What I'll show is that this is actually the same way. Then W minus W, which is 0 obviously, is equal to V1 plus dot 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 up to Vm minus V1 prime plus dot 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 all the way up to Vm prime, that whole quantity. Okay, agree with this so far? I've supposed that W can be written in this way, and I've supposed that W can be written in this way. So I'm just replacing the first W with that and the second W with that. Okay, now this is equal to, I should get rid of those bars so no one thinks I'm doing division. This here is equal to, well, now I'm just going to do a little bit of grouping. So V1 minus V1 prime plus dot 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 all the way up to Vm minus Vm prime. Since Vi minus Vi prime is an element of Vi for I equal to 1 through m, we get Vi minus Vi prime equals 0, since we've assumed that the only way to write 0 is in this way. That is, if 0 is equal to a bunch of, a sum of v's, then all those v's are 0. Here I've got 0 equal to a sum of v's, so all those zeros are, or all those v's are zeros. Hence, Vi equals Vi prime. Oh. And there is only one way to write W as a sum of elements of Vi for I equal to 1 up through m. Okay. That is V1 plus Vm is direct. Cool. Easy enough. We just proved that result. Let's see if we can do a little bit more. Okay, last result of the day. So, we just showed that if you have a sum, then it is direct. If and only if, the only way to write the 0 vector is as a sum of zeros, which you can always do. It basically says that that is the condition that you have to check to see if a sum is direct. So you've always got this one way to do it. You just have to make sure that there's no other way. And as long as you check that condition, then you're good to go. So here is one other condition that basically comes right out of that. So let's suppose that U and W are subspaces of V. Then the sum of U and W is direct if and only if, the two-sided arrow right there, U intersect W is 0. So the only time you have a direct sum of two subspaces is precisely when they only intersect at 0. Here's kind of the nice way of thinking about this. Let's look at R2. Here, I'll even try to use straight lines here. Yeah. Okay, here's R2 in a nutshell, right? Just imagine like the plane. Okay, I'll draw two different things that we already know are subspaces since we know the basics, right? All right, a subspace here will look like some kind of a line. Okay, here's one subspace. Pick any other subspace. It's got to be a line as well. Bada boom, the only time it's direct is when the only place they cross at, here I'll put a different color, is right at 0. Only intersect at 0. Okay, so let's prove this. First, suppose, and I'm going to start using this notation. If you're all right with it, it'll save me some time. And since I'm kind of slower at writing on a drawing tablet, I bet you'll ultimately appreciate it. Instead of writing suppose, I will impose a P on an S, superimpose a P on an S. So an S and then a little P right here. Suppose, that's shorthand for suppose. So let's suppose that U plus W is direct. If V is in the intersection of U and W, then 0 equals V plus minus V. Since V in the intersection implies that V is in U and V is in W, and hence minus V is in W as well. So, by the previous result, we have written 0 as a sum of things. V equals negative V equals 0. Oh, okay. Hence, since we've said, hey, pick anything in the intersection, oh look, it's 0. The intersection is precisely equal to the set with only the 0 vector in it. Certainly the 0 vector is in there in the first place, right? Since both U and W are subspaces, they must contain the additive identity of the larger vector space. So 0 is definitely in there. What we've shown now is that anything else that's in there, just through this argument, is also 0. So there is nothing else in there. Okay. Now, let's suppose U intersect W is equal to just 0. Okay. Then, if U is an element of big U and W is an element of big W, well, I'll say if U is in big U and W is in big W, and they are such that U plus W is equal to 0, then U equals minus W, just by the definition of additive inverses. Hence, U is in W as well. And I'll say that this is just since W is a vector space. That is, vector spaces have additive inverses for every element, and so W has an additive inverse. It is the element that if you add it to W, you get back the additive identity, so that is U. Hence, U is equal to the additive inverse of W, and since W is a vector space, it contains its additive inverses, and U is an element of W. Oh. But only 0 belongs to both W, big W, and U. This is just because we've assumed that their intersection is 0. So, W equals 0. Hence, U plus W equals 0 implies U equals W equals 0. And by the previous result, U plus W is direct. So let's break down this proof again, since I think maybe this is the more complicated one we've done today. In the forward direction, we said, hey, let's suppose we've got a direct sum. This means that there's only one way to write an element of this vector space as a sum of something from U and a something from W. So if we take something in their intersection, then we notice that we can add together that thing with its additive inverse, since if V is in the intersection, then so is its additive inverse. Oh, okay. By the previous result, this tells us that v equals to negative v equals 0, since the only way to write 0 in a direct sum is as a sum of two zeros. So the intersection is 0, since we took something in there and we showed it's 0. All right, cool. In the other direction, if we start with a 0 intersection, then we take two things, one from the first thing, another from the second thing, and then we add them together, and suppose we get 0. Okay, cool. You can definitely do this since both u and w contain the additive identity. So if u and w are 0, then you can get 0. So there's at least one case where you can do this. We're not supposing initially that we are in that case, but we know that it is possible. So this is not a silly thing to say. So by definition, this means that u is the additive inverse of w, since it's the thing you add to w to get back the additive identity of the vector space. That is, u is also an element of w, since w is a vector space and contains the additive inverses of its elements. So, since only 0 belongs to both w and u, by our assumption that their intersection is 0, this means that u and w are both equal to 0. Oh. Well, wait. We've just said that if u plus w is equal to 0, then u is equal to w, and both are equal to 0. That is, the only way to write 0 is as 0 plus 0, and so by the previous result, u plus w is a direct sum. Cool. Here's kind of the big picture. We've said, hey, you can have a vector space V. All right, and you can grab some little chunks inside of it. You can grab some like u's and some w's and so on. And if it looks like this, that is, if they are disjoint, then they are not both subspaces. In fact, what we have to have is we have to have a little bit of overlap. Okay, they have to have overlap at 0 at least. And what we've come to is saying, hey, look, when we form a larger vector space from these two things, the only time that doesn't contain redundant information, that is, the only time that it's a direct sum, is precisely when the only thing in that intersection is 0. All right, cool. So we've described how to take little pieces of a big thing that have the same property, how to put those pieces together into another thing with the same property, and when that process can be done without redundant information being present. So that is when you can sort of put them together without having too much overlap. You can put them together and they fit really nicely. We'll do a whole lot more things with sums and direct sums. It'll be a very important tool for us. But right now, let's call it a day. See you next time.